Good afternoon, students. Hope you guys are doing well. Today we are going to talk about subatomic particles, protons, neutrons, electrons. We're going to talk about atoms, both charged atoms and charged ions. We'll get a little bit of practice, and we're going to learn something called the Bohr model of the atom or the Bohr model of the ion, learn to draw those and get some practice in. Let me switch this to presentation mode so we can proceed. Your responsibility right now would be to make sure you got your packets out. In the back, there's some space. I will encourage you guys to take some notes down. Not everything that I write down will be important for you to get down, but I'll try to emphasize what is. All right. Okay. So we ended the last class period with a couple of these chart style problems, and you'll need, in order to fill these out with some confidence, you'll need your periodic table. You might even want a calculator to make the mental math go a little bit more quickly. So we'll just do two of these as a refresher. So if we're starting with lithium, we know that the elemental symbol for lithium is going to be Li. I'll put a number in the top left and in the bottom left here in a moment. The relative mass of lithium is going to be, oh, I got to get my own periodic table out. 6.9, which I'm going to allow you guys to round to 7 for the purpose of this problem. The number of protons that lithium contains is 3, since its atomic number is 3. As far as electrons are concerned, if we think that this is neutral lithium, and we can assume that it is in this problem, then our electrons will cancel out our protons. For neutrons, those exist in the nucleus, so there must be 4 for a total mass of lithium to be 7. The next one we'll take a look at the very bottom one. It tells me that the relative mass is 16. And if you look on your periodic table for all of the different average atomic mass numbers, the one that is closest is 15.99, which is oxygen. So I'm going to write oxygen in here. I'll note that the symbol is O. I'll note that the amount of protons is 8, since the atomic number of oxygen is 8. The mass is 8, therefore there must be 8 additional neutrons in the nucleus. And if this is neutral oxygen, there is also 8 electrons. I would like to change this for a moment, though, and say that what if this is oxygen with a charge of 2 minus? How would that affect the number of electrons? A lot of students are going to say 6. This would be a misconception. 2 minus means 2 additional electrons. So we're going to change this number to 8. Okay. I did forget to put the mass number up top, which is 16, and the atomic number below, which is 8. For lithium, it would be 7 and 3. Okay. Oh, did I make a mistake here? I think I did. Rather than it being 8, it would be 10. So if you caught that while you were sitting in your seat, good job. All right, moving on. Let's talk about the Bohr model of the atom. What do we need to know? We need to know that the electrons exist in these clouds, and they have specific energies, and lower energies are in lower shells, higher energy electrons are in higher shells. And they always fill up from smallest energy shells to higher energy shells. Okay, the first orbital shell, or ring, can hold up to 2 electrons. The second can hold up to 8 electrons. The third can hold a maximum of 18. And the fourth can hold a maximum of 32. Okay, information that we need to know to create a Bohr model. What's the symbol? What's the atomic number, mass, and then all of our P, N's, and E's. If we try to draw magnesium, the first thing you're going to want to draw is a nucleus. So this is where you guys would come in. And in your notes, you're going to draw a nucleus, right? We want to ask ourselves in the nucleus, how many protons and how many neutrons are there? So sit and think about that for a moment. Use your periodic table to try to answer how many protons and neutrons. All right, so there's 12 protons, which means I'm going to write the number 12p positive in the center. The atomic mass also happens to be 24.31, which you can round to 24. Given that the mass of the nucleus is 24, there must also be 12 neutral neutrons. Why don't I make this look a little bit better so that you guys can understand it more easily? 12 protons, 12 neutrons. Now, the next thing is draw out 3 or 4 electron shells. 1, 2, 3, 4. All right, remember that electrons fill in low to high energies. So how many electrons are we going to need, assuming that this is neutral magnesium? Neutral magnesium would contain 12 positive protons with 12 negative electrons. For your 12 negative electrons, you want to put 2 on the first ring, 1, 2. You want to put 8 on the next ring, 1, 2, 3, 4, 5, 6, 7, 8. And lastly, you want to have 2 on the third shell, 1 and 2. All right, I'll give you guys a moment to get that jotted down, but this would be officially the first Bohr model you have drawn for neutral atom of magnesium. Remember that magnesium's symbol would be 24 and 12. And this is the Bohr model, a nice, easy representation of magnesium's atoms. Let's move on. Okay, one thing I would like to note is that these 2 electrons in that third shell, since this is the magnesium Bohr model that we just drew, those 2 electrons are special electrons. Because they're on the outside of the atom, they're more susceptible to influences of other atoms. In other words, they're going to be the major ball players when it comes to reactivity. And reactivity relies a lot on what those outer electrons will choose to do, how they are going to interact with their neighbors, in other words, different atoms. So those 2 electrons, being that they're on the outside of the shell or the atom, are called valence shell electrons. You'll hear a lot of chemistry students or teachers just say valence electrons, VEs. These are the most important electrons in the entire Bohr model. Every atom will contain some amount of valence electrons. Those are the electrons, again, on the outer shell for that atom. In this case, magnesium has 2 valence electrons. Let's try another example. Fluorine. How many protons, neutrons, and electrons does fluorine have? Take a moment and look at your periodic table. We have 9 protons. Assuming this is neutral, we have 9 electrons. The average atomic mass is 18.9. I can round that to 19. That means, 18.99, that can be rounded to 19 for the mass. That means that we're going to have 10 total neutrons in the nucleus. Remember to first draw your nucleus. Note that there's 9 positive protons and 10 neutral neutrons. Next, you're going to want to draw 3 to 4 energy shells. 1, 4. I'll give you a moment. Go ahead and do that for yourself. and start filling in your electrons. 1, 2 on the first shell. Remember, it can only have space to fill up 2. The next is 8, maximum. However, I only have 7 remaining for a total count of 9. So I'm going to draw 7, not the full 8, for energy shell 2. Okay, we do not have to answer this question. That'll be in our next unit. This is the Bohr model for fluorine with a mass of 19 and an atomic number of 9. What if we have a charged particle, such as an ion? So, what would change if it was fluorine with a -1 charge? What we need to know is that fluorine has now gained 1 valence electron. So in our previous drawing, we would go from having 9 electrons to now having 10 total electrons with the same number of protons and the same number of neutrons. So the way that our Bohr model would then be fixed, and for sake of time here, I'm going to go ahead and come back to the original fluorine drawing. What would get changed is 1 extra electron. I'm going to put an X here to indicate that extra electron for fluorine -1. So it has gained 1 extra electron. With 10 electrons and only 9 protons, the total charge is -1. Let's try a different one. Sodium with a charge of +2. How many protons does sodium have? 11. How many neutrons does sodium have? 12. How many electrons does sodium 2+ have? Take a moment and think. Normally there's 11 electrons. However, there's a charge of +2. So in this case, we will have 9 electrons. 9 electrons compared to 11 protons would yield a charge of +2. The symbol would now become Na2+ with a mass of 23 and an atomic number of 11. Note that this is not what you see on your periodic table, but it is the most common isotope. 22.9 will round to 23. Go ahead and draw your nucleus. 11 protons, 12 neutrons. Draw some orbital shells. Fill in 9 electrons, 2 on the first shell and 7 on the next shell. All right. Be aware that some atoms can come in isotopes. Not all atoms of carbon are the exact same. Some atoms of carbon are heavier than other atoms of carbon. While this is the most common isotope, carbon does come in multiple versions. There is carbon-12, there's carbon-13, and there's atoms of carbon-14. When you look at your periodic table, you will know the most common isotope is the one that is nearest the average of all isotopes for that element. For carbon, if you check your periodic table, 12.01 will round to 12. Therefore, carbon-12 with an atomic number of 6 is the most common isotope of carbon. For a second, think about how the Bohr model for carbon-12 would compare and be slightly different than the Bohr model for carbon-14. Carbon-12 electrons would look exactly the same as carbon-14's electrons. Carbon-12 would have the same exact number of protons as carbon-14 as well. The only thing that would be different in the nucleus would be the total number of neutrons. I'll let you guys think for a second about which carbon would have more neutrons. Okay, that's the lesson for today. Get some practice with Bohr models. Thank you.